In this lesson, we shall focus on mathematics, MATH141, calculus, UKZN, techniques of integration, and a lot more. Okay, I depend on you for actually indicating what we need to do precisely this morning, because we were finishing Tat 4, and as we're finishing tutorial 4, there were a couple of things that obviously we had to discuss. And so it will be very important for you to sort of indicate the kinds of things that you think we need to do. Like if you look at the trig substitutions, in number 1, we have this particular question. Okay, we did this one by integration by part. We showed this one. And then number 2, we did the trigonometric substitutions. Okay, and then went on to look at the trigonometric substitutions. And then let us check now. Let us check. Went on to do 3 on the hyperbolic function. The fact that the hyperbolic sine of x is the ln of x plus the square root of x squared plus 1 for all x. But also we looked at the arc cosh of the ln of x plus the square root of x squared minus 1. So the difference between the arc sine and the arc cosh is the x squared minus 1 for x critical to 1. Evaluate using a trigonometric substitution, hyperbolic substitution that. Use part A to show that the above answers are equivalent. Okay, we did this one of 3B. So I depend on you as we're like skimming through Tat 4. Went on to look at the arc length of the ln x. We showed that it is this. The area of the surface of revolution, we showed that it is this. Number 4 and 5 we did. Let's check. Went on to look at the partial fractions, 6a, 6b, we've already done. But now, I depend on you in case you want us to revisit some of this and give them some attention. Like 6c and 6d, 6c and 6d. Six E and 6F. Six E and 6F. Right, number 3 to 8, Tat 5. Okay, let's check. Number 3 to 8, Tat 5. Let's check that one. Here is Tat 5. This is Tat 5. And this is number 1. Number 1. Two. Two. 3. Okay, let us look at number 3. Let us look at number 3, Tat 5. We're starting here. Right, let us look at the first question, 3a. This one here. Now, this particular integral is a very interesting integral, but also we need to look at exactly what we need to do. We need to look at exactly what we need to do to solve this particular integral. So to evaluate this, we need to look at the fact that 0 is problematic, because if you put 0 into the denominator, then it's going to become undefined. So 0 is a singular point. It's called a singular point. Meaning that now to integrate from 0 to infinity of dx over the square root of x1 plus the square root of x. To do this one, you would have to take the limit as epsilon approaches 0 from the right of 0 plus epsilon to infinity dx over 1 plus the square root of x. You let u be 1 plus the square root of x. 1 over 2 dx. Okay, we just need to do the integral here. And so to do this integral, you have exactly that. So that when you have the integral of dx over the square root of x, then you have 1 plus the square root of x. What is dx? 2 the square root of x du. Dx is 2 the square root of x du, the square root of x, and then this one is u. Okay. And if you check, it is clear, therefore, at this point that this one cancels, giving us 2 1 over u du. And this is 2 the ln, which is 1 plus the square root of x plus c. Okay, we continue. So now this is exactly what we have here. And therefore, this is the limit as epsilon approaches 0 from the right. Now, the integral of this is 2 the ln 1 plus the modulus. Okay, and then obviously this one is 0 plus that, so it's epsilon to infinity. Okay, but now the couple of things obviously that you need to take into account here. It is the fact that it is undefined here, but also it's going to be undefined up there. Or it is rather an improper integral as well at the top. And therefore, it means that you need to take all these into account. So you need to, in essence, involve 2 limits. You need to involve 2 limits. And so what we then need to do, you also need to involve the limit as b approaches infinity of the limit epsilon approaches 0 from the right. And then you'd have epsilon to b, like this. Exactly this way. And then you have dx over the square root of x1 plus the square root of x. Meaning this is the limit Okay, so we first look at this one, the inside. Because there are two things here. So the integral of this is the ln. The limit as b approaches infinity. Okay, let us check this one. So now, at this point, if you substitute everything here, it's a limit as epsilon approaches 0 from the right of 2 the ln of 1 plus the square root of b minus 2 the ln of 1 plus the square root of epsilon. And then you take the limit as this approaches. Yes, please.
Yes, may I ask, there by the infinity, why do we substitute b?
Please come again. The
By
b.
the infinity, why did we substitute b?
Okay, why didn't we substitute b? Because, anyway,
Why did we?
why did we put b at infinity? Okay, because integrals that have a limit of integration as infinity are improper because of the infinity as a limit of integration. But now, because of that, then always we must replace the b, the infinity by a b. Because the integral it's an improper integral of the first kind. But again, this one is an improper integral of the second kind. So it's like 2 in 1. 2 challenges in one problem. What is the first challenge? The first challenge is if you substitute 0 into the function, it's just going to become 0, the denominator. Meaning that at 0, it is undefined. Meaning it is an improper integral of the second kind. But also at infinity, it is an improper integral because of the infinity as the limit of integration. Meaning, therefore, we need to take care of both cases in ESADS. Okay, so now think about this. So now this is what we have. In other words, this means the following. Okay, so this means that whenever we have this integral here, which is the square root of x, 1 plus the square root of x, this is equal to the limit. It equals the limit as b approaches infinity, but there's another limit as epsilon approaches 0 from the right. B approaches infinity, epsilon approaches 0 from the right. To the ln of 1 plus the square root of b. One plus the square root of epsilon. Okay, now let's take the limit. First, we take the limit 1 by 1. We're going to take the limit as epsilon approaches 0 from the right. So it's going to affect only this one, but the b is not going to be affected yet. So you have 1 plus the square root of b minus 2 the ln of 1 plus the square root of 0. So this one becomes 0. Meaning we have the limit as b approaches infinity, just taking it step by step. So this is the square root of 0, which is a 1. Ln of 1, 0. So you're only going to be left with 1 plus the square root of b. But now we take the other limit as b approaches infinity. So it's going to be 2 the ln of 1 plus the square root of infinity. Square root of infinity is what? It's infinity. 1 plus infinity is infinity. Looking at the log graph, for infinity. It is clear that in the Cartesian coordinate system, or in our Argand diagram, this is y equals the natural log of x graph. But if we actually take the limit as x approaches infinity, this graph also approaches infinity without bound. And therefore, this becomes infinity. And therefore, it diverges. And therefore, it diverges. Okay, think about this and see if you have a question on this kind of problem. But it is an improper integral of both kinds, like of the first kind and the second kind. The first kind is this one. The second kind is the zero, which when substituted here, it's going to make the denominator zero. So we must actually include both cases. The b approaches infinity, but also the fact that this function is undefined at zero, because if ever zero is the limit of integration, but if you put it here, it's going to make the denominator zero. Okay, giving us a hint of one of the challenges we need to deal with in this problem here. And we move forward. We move forward. We move forward. We move forward. So it's something that you need to take note of here, as a matter of fact. Right, you need to take note of here as a matter of fact. Okay, we need to move on to the next question and see now what to do next. And see what to do next. Okay, let's look at the next one. Right, in the next question, we actually would be looking at instances where we actually obviously have a couple of cases that are important for us to take note of. Right. Now, in this problem, your teacher might use a different approach to this. Your teacher might use a different approach. Now, sometimes the most common tendency is to break it down as follows, this A part. Okay, because we can see that there's a problem at zero, but there's a problem at infinity as well. So there are two problems in this question. Okay, there is an approach that is often used in the textbook for this course. Okay, it's the analysis textbook that normally I use. So you can always break it down like this. You can take it 0 to 1, dx over, so these would be correct methods that look a bit different from each other, yet they converge in terms of the results, because the results will be equivalent to each other. Okay, yeah, you can break it down like this. And then now, because of the zero, we separate, but this one is infinity, so that we have the two limits that are separated. And so when we separate now, we can see that we can deal with the limit for this one, and then we put the b this side. So we just put the number 1, because at 1, then if you put 1 here, the square root of 1 plus the square root of 1, everything is okay. It's defined this. And then now you can take the limit as epsilon approaches 0 from the right of 0 plus epsilon. Okay. 0 plus epsilon. And then we have dx divided by 1 plus the square root of x. Dx. Oh, we've put the dx already for this one. So that is another way of doing the problem, because you already can see that the problem is at 0. So we just integrate from 0 to 1, because we know that between 0 and infinity, the number 1 is there. In principle, you can put any number, but the number 1, I'm trying to emphasize its commonality. It's popular. That is why they even use the 1 here. That's why they even use the 1 here. So if there's a problem with these kinds of integrals, we can break it into 2 pieces. And then now integrate from 0 to 1 and then 1 to infinity. Okay, we'll continue. We continue. Okay. So now then this one you're going to put the B. Okay. Okay, you have this one. So this one, you already know the integral. We did it on the other side. So it's epsilon to 1. And then you put the 1, because you see, even in your class, they put the 1 here, meaning you can break these into integrals that involve the number 1. So, and then when you get to this point, this one, you already know the integral is to the ln of 1 plus the square root of x. 1 to b. At this point, you substitute everything, and you have the limit. Epsilon approaches 0 from the right. You put the 1, which is to the ln of 1 plus 1 is going to be 2. To the ln of 1 plus the square root of epsilon. So it is to the ln 1 plus the square root of b. To the ln of 2. Okay, so now you take the limit here. As epsilon approaches 0 from the right, this one is going to be the square root of 0, which is 0, plus 1. So this is going to be the ln of 1, which is 0. And then you're only going to be left with 2 ln 2. Here you have the infinity. So this one is going to be minus 2 ln 2. Minus 2 ln 2. And then you have this one as b approaches infinity. It's going to be the square root of infinity, which is infinity. The ln of infinity is going to be infinity. But obviously, if you look at 2 ln 2 minus 2 ln 2, it's 0, giving us this and giving us infinity, and means that this integral here diverges. So I'm then saying, this is another way of doing it. Breaking it down to 2 pieces to avoid using like 2 limits in one problem, because now there are 2 problems. The 0 is a singular point because the function is undefined at 0, but also the infinity as a limit of integration is problematic. Why? Because this function, this integral is improper. It's improper at that infinity there. Okay, so let's move on to the next question. So we can break it into 0 to 1, 1 to infinity. Yeah? I hope that is clear. Correct. Okay, so let us move on to the next question. Let us move on to the next question. We look at 3b. Now 3b, the problem is 2 times also. The infinity makes it improper. But the 1, because if you put 1 minus 1 here, it becomes 0. Meaning that we have 2 challenges in one problem. Right, because you have 2 challenges in one problem, then we need to tackle these wisely. The question then is, what do we do in a case like this? Because still we have a problem. So we can use the 1 unit rule. 1 unit rule. What is the 1 unit rule? The 1 unit rule is you consider this one and just add 1. One of the ways we can use is to use what we call the 1 unit rule. 1 unit rule. Okay, what is the 1 unit rule? This is 1. And the problem is the number 1, but 1 minus 1 is 0, making the denominator 0. So we're going to add 1 to 1, getting a 2. Like this. Okay? So you can have this. And then you add. Then you have 2 to infinity. Dx over x, then you have the square root of x squared minus 1. All right, obviously now the problem is in 2 places. It's at 1 and also improper at infinity. In each case, therefore, you can do it twice. I mean, you can use the other first method I used, but I feel that maybe it's too cumbersome and it involves 2 limits that are just congested and very nested limits. So meaning that you can just break it down like this. You can just break it down like this. Okay, now let us look at this one. The question is, what is the integral here? We need to just do the integral very fast here on the side. But to do this integral, we're going to let the x squared minus 1. Right, and then when we get to this point, okay, so we continue. We continue. Right, so now in continuing, you have, okay, let's first find dx. Okay, so du, right, so you have the du, okay, let us see this one here. Okay, so when you're here, you can see that du is equal to what? 2x dx. It is 2x dx. Okay, so now if it is 2x dx, then what are you able to achieve here? Then you come here. What is dx? Dx. Okay. Right, so dx at this point. Okay, so this one you'd have to use another formula. You need to use another formula. So you'll use the following formula for the integral. It can be done in those particular ways, but there is a shortcut to this particular integral because it involves using another formula. Okay, so yeah, that's what we're moving towards. Okay, I'll just obviously give you now the formula for that we use here to tackle this kind of a problem. So to tackle this kind of a problem, we use the arc functions. So we'd have to use those arc functions, those inverse functions. And so I'm actually reverting to those just now because that is the way to do it. Okay, so just a second, just to save time, we're going to actually use the okay, just 1 second. All right. So this one is the arc Okay, this one you can say, generally there is a formula for it, just to save time and not have to need to know the arc formulas, which involve the square roots. So there's a formula, and there are two formulas. First, let's state this formula here. So whenever you have 1 over x squared minus 1 dx, arc secant plus c, so we'd have exactly this one here. And so okay, also when you have the okay, but also when you have the arc cosec integral.
Sure.
Okay, good. Okay, we are just 1 second. Just 1 second, I'm gonna be here. Okay, there are some formulas that I want to cite. Okay, this one is arc the secant. Right, and so if you have a couple of other integrals, just 1 sec. I want to give you other formulas here that you need to know. That you need to know. Okay, so this is going to be the arc secant, but I want to cite another formula. Just 1 second. Just 1 second. Just 1 second. Just 1 second. Okay, I will okay, I wanted to say this. Okay, there are two of these, but there's this one here and also this one. 1 over x squared minus 1. If there's a negative here, if there's a negative, we then say it is arc the cosecant of x plus c. Okay, so right, so now we're gonna use these two formulas because of the fact that we know this particular integral here. So then we're gonna do the limit. Epsilon approaches 0 from the right. Right. Okay, we continue, please. So this one is going to be 1 plus epsilon. And then you have the limit. Now we put the b here because of this infinity limit of integration, making this integral improper, making it an improper integral. So we have the limit as epsilon approaches 0, but approaches 0 from the right. Okay, this integral you already know it is because it is there's a sort of a plus associated with it, a plus. So you have the arc secant of x. Like that. And then it is 1 plus epsilon 2. B approaches infinity. Two to infinity. Which is arc secant of 2. Which is B. Okay. So when B approaches when epsilon approaches 0 from the right, you have arc secant of 2. Arc secant of 2 minus arc secant of 2 is going to become 0. Leaving us with this one. And this one is going to be minus arc secant of 1. When epsilon approaches 0 from the right, it's going to be arc secant of 1. And then you're also going to be left with this one, arc secant of infinity. Arc secant of infinity. What is arc secant of 1? What is arc secant of 1? Arc secant of 1, there's a time when this secant is 1, and arc secant of 1 becomes what? Becomes a 0. Okay, just check this one out. Arc secant of 1 is 0. Then what is arc secant of infinity? When is the secant infinity? So these are the things you need to check. So there is arc secant of 1. What is arc secant of 1? Arc secant of 1 is a 0. Why? Because the secant of 0 is 1. So arc secant of 1 is 0. But what is arc secant of infinity? Arc secant of infinity, this one is actually exactly pi over 2 radians. So this is pi over 2 radians, making it finite. Making it finite. So that is something that you need to think about here. Okay, so indeed, okay, they wrote pi over 2 also. So the answer is indeed pi over 2 here. But once again, it can be done like this, but I feel that this is easier. What you call the 1 unit rule. You can just use the 1 unit rule. If you see like 2 problems, like the problem is at 0 here and the problem is at infinity. So you add 1 to 0 so that you integrate from 0 to 1, 1 to infinity. Here, the problem is at 1, the problem is at infinity. Why is the problem at 1? If you substitute 1 here, it becomes 1 minus 1, making the denominator 0. Meaning there's a problem here. So we're going to, okay, let's see what you're saying. Okay, how did we manage to get 2 for the interval? Okay, we got 2 by using what you call the 1 unit rule. What is the 1 unit rule? The 1 unit rule means that if there's a problem at a limit of integration, you can add 1. You can add the number 1 to get 2. Because you add the number 1 so that here you have 1 plus 1. 1, and then the next one is 1 plus 1, which is equal to 2. And then this one, then you're going to start from 2 and then run up to infinity. So this is the correct way to reason. And I feel that this is much more standard. Much more standard. This is called the 1 unit rule. So you add 1 to the problematic number. The problematic number, which is 1, 1 minus 1 produces 0. We're going to add 1 to it. So you add 1 plus 1, you get a 2. But also here, we'll have a 2 to infinity as well. You'll have a 2 to infinity. So this is called the 1 unit rule. 1 unit rule. That is how we get the 2. How did you get the 2? You take this number 1, add 1 to it to get a 2. Why do you add 1? We add 1 so you can break it into 2 pieces. Why do you break it into 2 pieces? Because it has infinity, but also there's a problem at the number 1. When you substitute the number 1, the denominator becomes 0. Meaning you need to take care of both of these. You need to take care of both of these. You need to take care of both of these. Okay. So let us see now what we can do. So now we're going to move to the next question. The next problem is problem C. But in problem C, we have two problems. So to integrate this one here, which is 2 minus x, to integrate this one here, there are two problems. One is at 1. Because if you put the number 1 here, it's going to be 1 minus 1. The denominator becomes 0. Yeah? So there's a problem at 1. But there's a problem at infinity also. So you must use the 1 unit rule. You must use the 1 unit rule. What is the 1 unit rule? Because this number is 1 is the biggest number, you must minus 1 from 1. Minus 1 from 1. If you minus 1 from 1, what you get? You get a 0. Meaning that you would have to integrate from minus infinity to 0. And then you have 1 minus x. You have 2 minus x. Then you integrate from 0 to 1. Using the 1 unit rule. And this is what you're able to achieve. Okay, here we're using the 1 unit rule. Like this. Okay. All right. Now, what is then the integral here? So you need to look at this integral and think. And see what this integral is. Okay? Because now, you manage to break it into two pieces like this. By the 1 unit rule. Because now the problem is at 1. And 1 is the biggest one. You're going to add 1. But you can't add 1 to 1 because it's going to become 2. And 2 now, this is the upper limit. It's the greatest one you can integrate up to. So you can't go up to 2. You can take a number in the middle. But between minus infinity and 1 on the number line, if you have minus infinity and 1 on the number line, there is a number 0. Between a negative number and a positive number, there is 0 there. When you are running from through the negative numbers, minus 2, minus 1, then there is a 0 and then a 1. So it's something to think about. Okay, we continue, sorry. So now, but now the next thing is we need to think about the integral. The question is, what is this integral here? Okay, this one, you need to evaluate it by substitution. You need to evaluate it by substitution. And the way to do it, you can just simply let. You can let u be what is under the square root. Be 1 minus x. So that du is minus dx. And then you'll have the integral of dx, which should be minus du divided by, here it's going to be the square root of this, which is u to the 1/2. 2 minus x. 2 minus x is what? So if you have u is 1 minus x, then you can add u plus 1. plus 1 minus x. Or you can just make x the subject of the equation. So u plus 1 is 2 minus x. So wherever there's 2 minus x, you put u plus 1. Like this. And then you have this. The question is, what is this integral here? Okay. So this integral here is, okay, let us check this integral, please, and then we shall continue. So it is 1 over the square root of 1 minus x. And then you have 2 minus x. You have 2 minus x. Okay. Right, so you need to think of the right substitution to integrate these. And one of the ways you can use to actually integrate these is exactly what? You can use the tangent. So this would be arctangent. It will be arctangent, so you can use this, is going to be 3 over 2, and then u to the 1/2. Okay, yeah, let's just use that one. So you can use the substitution that says u is the square root. What is this? Let's find the derivative of this. Which is 1 over 2, 1 minus x dx. So you find this integral here. And then if you find this integral here, which should be du 1 over 2 u dx. Okay, let us just do the integral for now, because it's going to involve a little bit more work. So you have the dx 1 minus x, 2 minus x. Okay. To deal with this integral, then we're going to have exactly the u here. And then you have the 2 minus x. Okay. What is 2 minus x? You square both sides from this point. Getting u squared is 1 minus x. Meaning x is 1 minus u squared. Wherever there is x, you put 1 minus u squared. What is the x? Which is 2u du. So you have this one. You have 2 minus 1, which is 1 plus u squared. These two cancels, giving us 2 du over 1 plus u squared. Aha. There it is, there it is, there it is, there it is. So what is this? If you start from here, you'd have 2 arctan of u plus c. That is the integral. 2 arctan. What is u? It's exactly this. 1 minus x plus c. Okay, so this is the answer. Okay, but now check. So the derivative of this is going to have a negative. Going to have a negative. Negative. And then it's going to have a negative. It's going to have a negative. Okay, then you have this answer. So this is the answer for, okay, it's not the final answer yet, but it is just the integral that we need to get. So it is minus 2 arctan u plus c. Okay, we take this one. We already know the integral now. In other words, using what we call the 1 unit rule, we integrate from minus infinity to 1 dx over 1 minus that 2 minus x, which is minus infinity to 0 dx divided by the square root of 1 minus x 2 minus x 0 to infinity divided by 1 minus x 2 minus x. Okay, so we know this integrals already. So the problem here is at infinity, and the problem here is, well, it's at minus infinity because minus infinity is it makes the integral improper. We must use b. And also we actually have that we have a problem at 1 because there's 1 minus 0. So we're gonna okay. I mean here from 0 to 1. From 0 to 1. So using the 1 unit rule to separate this integral, to break it into pieces, you need to integrate from minus infinity to 1 minus 1. Meaning you have the limit. You have b approaches infinity with minus b to 0 dx over 1 minus x 2 minus x. Okay, here then, because the problem is at 1, you must use epsilon. Epsilon approaches 0 from the right, and then it's 0. You have 1 minus epsilon dx divided by the square root. 2 minus x. Okay. What is the integral here? The limit as b approaches infinity. What is this integral? Let's check. We already said the integral is minus 2 arctan u. But I wanted to also say here, it's minus 2 arctan the u is the square root of 1 minus x plus c. So that is minus 2 arctan 1 minus x. 0. And then you have the limit. Epsilon approaches 0 from the right. So which means that minus 2 arctan of 1 minus x, 0 to 1. 1 minus epsilon, yeah? Okay. Okay, now let's substitute the limits. Arctan, if you put 0 here, it's going to be arctan 1. Because there is a minus, then it's going to be plus. 2 arctan, if you put in the place of x here, it's going to be minus minus b, which is going to be positive. 1 plus b. The limit, epsilon approaches 0 from the right. Arctan. You put, in the place of x, you put 1 minus epsilon here. 1 minus epsilon, but it's 1 minus 1, it's going to be 0, giving us only epsilon. 0 plus 2 arctan of 1. Okay, if you put infinity here, what is arctan of 1? Arctan of 1 is 45 degrees using a calculator, pi over 4 radians. And if you come here now, you put infinity here, it's going to be arctan of infinity, because if you put infinity in the place of b, it's going to be infinity plus 1, infinity. Arctan of infinity is pi over 2 radians. Okay, minus that. Arctan of 0 is 0. Okay, let's see now what we're getting. This minus 2 pi over 4 and the 2 pi over 4, they give us 0, and this one would give us exactly 0. And then we're left with this one, 2 cancels, giving us pi. Aha, there it is. So right, this pi, this pi is this infinity, so which means that the integral converges. The integral converges. Any question about the C? The C was a little bit tricky. What was tricky about it? Well, I mean, the pattern of 2 types of integrals, improper integrals of the first kind and improper integrals of the second kind. So improper integral of the first kind Improper integral of the first kind. Improper of the second kind. So okay, so now we have the following, yeah? That is answer. Think about it and make sure that you're able to understand what is happening here. Right, make sure that you're able to understand what is happening. Right, yeah, okay, yeah. Make sure you're able to understand what is happening. Yeah, I'm having my class now. Yeah, can you please text me because I'm having my class now. Yeah, I'm speaking to someone. Yeah, please text me because I'm having my class so that I can understand your problem or your challenge, so that I can see how we can assist. Okay. Okay. Um. Okay, we continue, please. I'm just trying to attend to speak to this person here. Because now they just telling me that they actually need an intervention. Okay, but now take a look at the three. We've done the 3C. It converges because the integral is pi, and we got pi as well. But take note of the steps we have gone through. Okay, so now we continue to the next question. We continue to the next question. Continue to the next question. Okay, yeah, we are here, please. We're here now. We're here now. Right, we are here. We are here. We are here. Right, we are here. We are here. We are here. Okay, okay. All right, we are here. We are here. We are here. We are here. Okay, just deciding which one to do next. We're deciding which one to do next. Point. We want to decide which one to do next. Okay. Want to see which one to do next. Okay. Good, good, good. We are seeing which one to do next. All right, all right, all right, all right, all right, all right, all right. Okay. Okay, now let's look at number 4. Consider the integral of this one here from 0 to 1 of dx of x to the power p. Prove that this integral converges to this if p is less than 1 and diverges if p is smaller than 1. Let us look at this particular integral here. So now you'd have to look at this involves something we call the p series. P series. And there's something called the P series test. P series test. Right, so let us take care of the P series test and see what we can do here. Right, and see what we can do here. Okay, in view of the P series test, we need to perform integration and see precisely then what to do in a situation like this one here. Right, and see exactly what to do in a situation like this. Okay, let us continue to check what to do here. And see what we need to do here. Right. Okay, we continue. Okay. Let us pay particular attention to this and see what we can do. And see what we can do. Okay. What then would we have? Okay, if we consider this particular integral and look at the cases that this integral converges if P is less than 1. So one way to do that, you can say, let P be less than 1. So that's sort of case 1. So if P is less than 1, you'd have to look at this particular integral, but also, yes, please. Oh, yeah, okay, yeah, that's fine. So that's okay because, yeah, I've tried to attend to your issue. So yeah, just check your messages, please. Okay. Okay, so we continue. Okay, yeah. So this is one dx of x to the power p. And then, obviously, what is the problem here? The problem here is the 0, because whenever x is 0, then it's going to be undefined. Yeah? So now we must be able to deal with the 0. And to deal with the 0, we do what? To deal with the 0, we will have the limit epsilon approaches 0 from the right, dx over x to the p. Okay, so which means that we have the limit epsilon approaches 0 from the right. Dx. You add 1 to that, which is 1 over 1 plus minus p x to the power minus p plus 1. We have the limit and we take everything into account. So we have the limit which is dx over, which is the limit Okay, so now you can just take out the, you can just take out the minus, the 1 over that, the 1 over the expression in terms of P. Which is minus P plus 1. So what are we able to achieve out of this? So this one, you can even take this out. The 1 minus p, you can take it out because the constant. Minus this. Okay, let us check this out. So p is less than 1. Meaning that p can be 0, making this a 1. And if p is less than 1, so now this is going to become what? 1 over 1 minus p. And then when you take the limit here, this is going to be exactly what? 1. Because this one, epsilon approaches 0 from the right, then it's going to become 0. 1 minus p. Hence, you have the integral from 0 to 1 of dx. Okay, so we continue. Right. Okay, let me just speak to this person. Just 1 minute, please. Hello? Yes, how are you? Yes, are you seeing the people there? Are you there in the 717 Martinez? Yes. Yeah, they are possibly coming out. Okay, bye. I'm sure they're the ones. Yeah. Okay, bye. Okay, sorry. I was just speaking to someone here. So that now at this point, what you have then this one. 0 to 1, then x to the power p. So okay, so this becomes the answer. So obviously this is the case if this is the integral if p is less than 1. If p is less than 1. But now we need to do the other one when p is greater or equal to 1. So let's check that one out. So this one is case 1. Next is case 2. Case 2 is let p be greater or equal to 1. Right, let p be greater or equal to 1.
Sometimes he's not sure. She's not sure.
Okay. Let me see. Okay, just 1 minute. I'm trying to see if this person is telling me this and that. Just 1 second. I'm trying to just see if I can give this person some attention for a minute. Let me see. 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 Right. Let me see. Let me see. Let me see. Um. Okay. Right. I'm trying to see if okay. Now, whenever we let p to be greater equal to 1, then what is the problem with this integral? So we need to integrate from 0 to 1. Which is x to the power p which is x to the power p okay, but yeah, p is greater equal to 1, so in which case let us, well, considering this case here, but the problem is still at 0 first, because whenever x is 0, then this is undefined, so we need to take the limit. Is an improper integral of the second kind, which is undefined at a limit of integration. So you have therefore that you have the following now. You then have the following here. You then have the following. Epsilon approaches 0 from the right. And then you have this integral here. 0 plus epsilon to 1, and then x to the minus p dx. Which is the limit okay. You have integrated this one, and then now we have epsilon to 1. Okay, you can even do it. We should have done it in one step and then broke it into two cases. There are many ways to do it. Anyway, right. So we are here now. But now, first, let us substitute the limits of integration. And in the meantime, we keep the limit. And then you substitute here, which is 1 to the minus p plus 1 minus epsilon to the minus p plus 1. So this is what we have. Okay, now let's check what happens here. Whenever p is bigger or equal to 1. Okay, this one, either way, like whenever p is 1, it's going to be 1 to the minus 1 plus 1, 1 to the 0. Whenever p is bigger than 1, it's going to become what? Maybe p is bigger than 1, maybe 2. Minus 2 plus 1 is going to be 1 to the minus 1, giving us a 1. This one, whenever p is 1 here, it's going to be epsilon to the 0. P is 2, it's going to be minus 2 plus 1, which is 1 over epsilon. If P is 3, it's going to be epsilon to the minus 3 plus 1, which is e to the minus 2. E to the minus 2. Okay, which is 1 over e squared. In other words, this is the limit. Epsilon approaches 0 from the right. 1 minus p. So either way, this is 1 minus 1 over epsilon to the p minus 1. And this one, you put 0 here. When this p is very large, you put 0 here. My p is maybe 100. It will be 100 minus 1, which is 99. Then, this epsilon to the power 99. And then if you take the limit as epsilon approaches 0 from the right, then it's going to be 1 over 0. Okay, which is undefined infinity. But how is it infinity then when epsilon approaches 0 from the right? Obviously, it resembles a special type of function. I want to speak about a function, then we shall conclude. Please, just 1 second. Because the top is a constant. Like when p is 3, when p is 3, it's going to be, when p is 2, make p 2, and then it's going to be 1 over e to the p minus 1, which is 1 over 2 minus 1, which is 1 over epsilon. What kind of a graph is this? This. So, when this is the case, this kind of graph, when epsilon approaches 0 from the right, when we approach 0 from the right, this is 0, the origin, from the right, this graph approaches plus infinity. So that it's 1 over 1 minus that. 1 minus, so this thing here is going to approach infinity. Going to approach plus infinity, but there's a negative there. And therefore, this whole thing is infinity. This whole thing becomes infinity. So obviously, it means therefore that these diverges. This is called the there are those integrals that are like these that involve the p. Okay, there's something called the p series. Okay, yarn, because we're going to speak about the tests. P series will be 1 over n to the power p. Yeah, and it's a summation. So it's 1 over n to the power p, but you see this summation is 1 to infinity. That is a summation. But this one here is a way of showing that obviously this P series has some divergence. There's some divergence whenever P is greater or equal to 1, but whenever P is less than 1, then this is what you have. Okay. So yeah, think about this and make sure you understand this. Okay, because it's hinged on what we call the P series test, and then something called the integral test. The integral test. So we'll discuss the tests. Yeah, the integral test will run up to infinity. Will run up to infinity. So, but obviously this one is limited to 1. But the integral test will run up to infinity. Infinity being the upper limit of integration there. Obviously, it becomes therefore an improper integral in case we use the integral test. Let's move on to the next question. Suppose f and g, so now we have number 5. Suppose f and g are continuous functions. Suppose f and g are continuous functions, and that this is the order of the functions. The function f is less or equal to the function g, but the function f is bounded below pi 0, above pi g. So this f is a bounded function. For x greater equal to a, we can show the following. If this integral from a to infinity of f of x diverges, then the integral of g of x also diverges from a to infinity. If this integral here converges, then this integral here converges. And because f is less than or equal to g, then this integral here is also less or equal to the integral of g. Okay. So now, the couple of ways, obviously, we can use to do this particular integral. Okay, now I want us to look at this, but very, very carefully, this particular problem. This is our TAT. It's exactly TAT 5, and I want us to discuss it in some detail. We need to look at what this means. We need to look at what this means. Okay, this is called the comparison test. So now we're going to use what we call the comparison test. But now we're going to state the comparison test here. Just a second. We're going to state the comparison test in a second, and then we shall use it to do this particular question here. Right, we shall have a statement of the comparison test. Okay. Right. We shall have a statement of what we call the comparison test. Comparison test. Okay. First and second. So there are 2 of them, and then there's another one in 248. Okay, just 1 second, because I want us to discuss this here. Okay, there's something called the comparison test for integrals. Comparison test for integrals. So we're just going to look at the statement and then we shall use it. Comparison test for integrals. Let f and g be defined on, yes, please. And then you have a to infinity and Riemann integrable. and Riemann integrable on A to B for every B bigger than A. Moreover, you suppose that the integral of f of x gx for all x greater or equal to A and B from 0 to that dx converges. Then the integral from A to infinity also converges. Okay, let us discuss this theorem called the comparison test for integrals. Let f and g be defined on this interval from A to infinity, and Riemann integrable on the closed interval from A to B for every B bigger than A. Suppose that f and g are ordered in that manner for all x bigger than A, which is exactly what has been said. This one here is a theorem. It's a theorem, the one I'm giving in red. It's not just anything I'm writing. It's a theorem. This is the rule we use. Suppose, therefore, that the f and the g are ordered like this for all x be equal to A, and also this integral converges. If this is the case, then this integral converges. Okay, then this integral converges. Right, so ordinarily we will use this particular result to show this here. So now what we then do here, this is how we do it. Now, because we know this, so now we know that 0 is less or equal to f of x is less or equal to g of x. Okay, this we know. For x bigger or equal to A. Then now we can be able to see that this is less or equal to, then you can take the integral of f of x dx from A to n, which is less or equal to the integral from A to n of g of x dx. This is true since 0 is less or equal to f less or equal to g. Okay. Right. Now, right. Okay, I want us to look at this. So now we need to look at this and reason from this point. But this one diverges. So the f diverges. And this is what we We then say since okay, since this is the case, we come to this. The integral of a to n f of x dx. This one diverges as n approaches infinity. So this one either becomes infinity or becomes minus infinity. So it diverges. So what we're then getting is that we then have infinity is smaller than this. As n approaches infinity, of course. As n either infinity or n. Okay. But as n approaches infinity, then this n becomes infinity. But we are told that this integral of f of x, this one here, diverges as n approaches infinity. Hence, okay, look. Now, if this one diverges, so the smaller one diverges. On this thing, this integral is greater than or equal to infinity. If it is greater or equal to infinity, it means also this one must diverge. Hence the integral, this one, hence this integral here because of this inequality, it is, hence this integral here is greater or equal to infinity. Right, meaning this integral, hence this integral is unbounded. It's unbounded. And then thus this integral from a to infinity of g of x dx diverges. The fact that it's greater or equal to infinity means that it is unbounded. You can say it is unbounded as n approaches infinity. Can write here, it is unbounded as n approaches infinity. So we've proven this case here. Moreover, if the big one converges, so yeah, if the smaller one, if f converges, rather if f diverges, then g diverges. But if g converges, the big one converges, then f also converges. Now, the integral of a to n. Okay, yeah, we start off, okay, now we are looking at the second bullet point, this one. The f that is this. Okay. So now we have this. And then we then say, since this fg, then you have the integral since this, but this integral of g of x increases to its limiting value. Limiting value as n approaches infinity. Okay, we can continue here and then say hence. Hence the integral from a to n of f of x dx is increasing. Is increasing and bounded above. So because this g is increasing, but it increases to its limiting value because it converges, this integral. So if this integral converges, you can imagine that this integral is to its limiting value. So it has a limit. So you have therefore that you have the integral from a to n of f of x dx, but there is a limit of this. So it means therefore this one is increasing and is bounded above. This is a bound because of the convergence of the g integral. So this is bounded above. Hence the integral from a to infinity is a convergent integral. It's a convergent integral Okay, try to follow the steps. Quite a very general proof here. Convergent integral. Okay, this is how you would generally be expected to prove this. Okay, this is the theorem. So I'm just following the proof of the theorem. It's a theorem in the textbook. In the textbook. So I'm not reinventing the wheel. This is the proof. From here, then you go like this. This is just a comment. Okay. What have we done in the second part? So now to prove this second bullet point, we then said we take now the function f is a bounded function between 0 and g. You take the integral both sides. Since f is this, the integral of g of x dx increases to its limiting value as n approaches infinity. Hence, this integral is increasing and bounded above. So this one, because this one is convergent, it increases to its limiting value by dint of it being convergent. If this is convergent, the g is convergent, it means that this is finite. You can say this. The g is convergent, it means it has a limiting value and therefore it's finite. Hence, this f now, this creates an equation like this, an inequality like this, which means that hence now the integral from a to n of f of x dx is increasing and bounded above also. And hence, this integral here of a to infinity is a convergent integral. That's what we want, that this converges. And this integral is the case. And this integral is the case. Okay, because this is convergent, f is convergent, and g is convergent, but f is less than or equal to g. Okay, look, you have f. Okay, so because of this, then you can take the integral from a to n, And this therefore implies that you can take the limit as n approaches infinity dx dx. Okay, so then you have that this integral here, this is the case. And obviously, you can just moreover say that therefore this is the case, yeah? This is the case, so that we have this. Because these both converge, it means therefore these integrals converge. These integrals converge. G converges being the biggest one, therefore f is also going to converge. I think it's 8:03. Should we take a break and then we'll continue later on? You let me know then when you're free again. What do we do? Please advise. Please advise. If we continue now, or we okay, let me check. Okay, good. We continue later. That's fine. So please, we depend on you. Then you let us know during the day whenever you're free. Then we can do other questions. Yeah, this was just a general proof, in which case, therefore, you need to just make sure that you repeat until you understand, until you internalize exactly sort of what's happening here. Okay, but we're going to make the recording available in the next couple of minutes. Thank you so much for joining us. It was awesome having this discussion. Until later on, take care and goodbye. Goodbye. Right.